Okay, welcome back to the Probability and Analysis webinar. It's a pleasure for me to introduce our speaker today, Taryn Flock from Macalester College. She's going to talk about extremizers for spherical extension exist more often than not.
Hello, so thanks so much for the invitation to speak here at PA. It's really nice to have a chance to give a seminar talk that doesn't require a ton of travel. And so today I'll be talking about extremizers for spherical extension, and the key question being, do they exist? Our answer is yes, often. And this is joint work with Betsy Stovall at the University of Wisconsin-Madison. So I hope that this will be reasonably informal. Feel free to interrupt if you have questions. I'm not great at looking for raised hands, so feel free to just unmute and ask. And with that, here's the plan for the talk. So I'll be talking a bit about sharp Fourier extension. That's the umbrella for what we're talking about today. I'll give a little bit of an intro to Fourier extension and Fourier restriction, and I'll talk about a bit about the history, at least in the case of the sphere. And then I'll give our results, and I'll talk a bit about our proof, the key tool being a profile decomposition. And so I'll state those profile decomposition theorems in with the proof. Here's our friend, the Fourier transform. What do we know about the Fourier transform? We know that if I take a function that's integrable and compute its Fourier transform, I get something that's bounded and is continuous. If I take a function in L2, well, what I get out in the image is something in L2. The Fourier transform is a bijection on L2, so any L2 function is possible in that image. But we don't have such a nice characterization of the image if I start in other LP spaces, right? The L1 and L2 results give me a whole family from interpolation where I could think about the question of what is the image of the Fourier transform? And we don't have great answers. So one question you might ask about these functions in the image is, can I restrict them to a manifold? The motivations for asking this question come from PDEs. It's certainly not the first thing you'd think of if you wanted to characterize the image of this operator, but it is something you can ask. In L2, you can't actually ask, right? I have a function, it's L2. It's only defined up to its values almost everywhere. So restricting it to a manifold, a lower dimensional set, a set of measure 0, isn't going to work. But for my L1 function, where the image is a continuous function, this restriction is very nice. So this leads to the question, for what pairs P and Q is such a restriction estimate possible? And the insight, the classical insight that gets this all going from Stein is that if M is curved, if I have a curved manifold, non-trivial estimates are possible. I can move beyond this L1 range. And it turns out that sort of the specifics of the manifold do matter. If I have a compact manifold, I get a wider range of possibilities. If my manifold has full non-vanishing Gaussian curvature, I again get a wider range of inequalities than if I have, say, the case of the cone where there's a vanishing curvature. Things are a little bit flat. Questions? I don't know if this is old hat or new, so if you have questions, feel free to jump in and ask. So the perspective that I'll actually be talking about today is the adjoint problem. What do I mean by adjoint? I really do mean sort of this, if I pair the operator acting on the function with a G, and I think about moving that operator over, what would I get? So the function restricted to the manifold would get paired with a function that lives on the manifold. So I'm taking, this is a little confusing because I've switched back to F here, but a function that lives on the manifold, and then we get out a function that lives back on our D+1. So this operator takes a function that lives on the manifold and extends it to a function on our d+1. So we call it the extension operator. And you can find that this is the formula for the adjoint in the case where my manifold is the d-dimensional sphere. And for the purpose of being precise, the measure that I'm taking on the sphere is the d-dimensional Hausdorff measure, so familiar surface measure. So in this setting, again, sort of duality gives me a family of exponents, or we can look directly at the formula. We find that there is a trivial estimate when the function is integrable. And because the sphere is compact, Holder's inequality lets me extend that inequality for any value of q, rather than just q is equal to infinity. So let's take a moment to talk about this diagram that I'm drawing here, because I'm going to draw a lot of these for visualizing these exponents, p and q, where our extension inequality is valid. On the x-axis, I have 1 over p. 1 over p is easier to look at than p because p is going to go off to infinity, whereas 1 over p stays between 0 and 1. On the y-axis, I have 1 over q. And so we can think about each inequality as some point in this space. As I was saying, we have our trivial inequality. Holder's inequality gives me the entire bottom line of this trapezoid. Then the classical L2 theory, and now since we're on the dual side, P can be 2, unlike restriction. If I'm dealing with extension, the barrier now from the L2 bijection stuff is taking Q to be half. We can never get there. We know that much. But the classical L2 theory tells me that for P is equal to 2, I have a valid inequality where Q is dimension plus 2 divided by 2 times dimension. And interpolation will let me fill in a whole trapezoid of true inequalities. The restriction conjecture, the extension conjecture, is that I can actually go up as far as where I hit the line, the symmetry line. So we can go up as far as Q d plus 1, 2 times d plus 1 over d, but we don't expect to actually be able to achieve that value for Q. And it's known to be false in the gray region. We hope that it's true for the yellow part, and it is the work of much ongoing progress to try to fill in exactly where this threshold is. The best results, to the best of my knowledge, are Guth, Wang, or some subset of Hickman, Rogers, and Zoll, depending on dimension. So this is our sort of crash course in the extension and restriction problems. Are there questions before I move on to talking about what I mean by sharp Fourier extension? If not, what do I mean by sharp inequalities? Different people mean different things. What I mean is that hopefully we actually have the best value for this constant C. Not just the best dependence on some parameter, but the actual best value. That's a bit of a dream. In many cases, that's a very hard question. So what can you say? What is this constant C? Well, it's the operator norm. That much I know. It's the operator norm of the extension operator. And so it's the maximum or the supremum over the sort of functions with unit norm in LP of their extensions. We can also ask, is this supremum a maximum? Is there a function that actually achieves equality? If they exist, can we say nice things about them? Can I give you a formula? Can I say that they're infinitely differentiable? And also, right, if we think about operators back on vector spaces, the unit ball here would be compact. So I'd be guaranteed existence of an extremizer. I'd be guaranteed some function that achieved equality. I'm going to keep using this word extremizer. So let's write down what it means. Extremizer is just a function that actually achieves equality here. So if I had a sequence of functions whose extension norms approach this supremum, is it possible to extract a subsequence that converges? That depends on an extremizer existing, but if it does, we can hope for this sort of convergence, this sort of compactness. Okay, the unit ball in LP is not compact, we know that. And certainly there are symmetries of these problems that mean that it's possible for these sequences to just bounce around. We have modulation symmetry in particular on the sphere. But if we control for the symmetry, can we find subsequences that converge? And that's the question that we'll really be focused on talking about today. If I have a sequence that's LQ norm is approaching the optimal value, can I extract subsequence that is converging? And by doing that, can I prove that extremizers exist? So this question has been asked for Fourier extension in the past. So there's some nice results. The two that are most relevant for our talk today are Fanelli, Vega, Visilia, show that for the L2 theory, as long as I'm below what I'll refer to as the scaling line for tradition, even though we don't have a true scaling symmetry on the sphere. So if I'm on this blue line here, where P is equal to 2, but Q is smaller than the classical L2 estimate, we do in fact have that extremizers exist. And we can say a little bit more on the scaling line. One of two things happens. Either extremizers exist, or extremizing sequences concentrate in a very particular way. So if you look at your sphere, you look at your neighborhood, and it's the sphere, it has symmetry, so there's something a little bit weird where we have to consider antipodal pairs. But if you zoom in on the neighborhood, extremizing sequences look like extremizing sequences for the parabola, is what Frank Lube and Sabine are able to prove. So they do not, however, show that extremizing sequences can concentrate. So it's possible that this dichotomy actually resolves into extremizers always exist. We don't know of examples where they don't. And in particular, in low dimensions, this dichotomy does resolve into extremizers existing and concentration not being a possibility. So that work is in a series of papers. Kristen Shao in 2012 look at the case where the dimension is 2, P is 2, and Q is equal to 4, which is very nice. We like even exponents in this business. And in that case, they're able to show both that extremizers exist and that they're infinitely differentiable. And that was followed up on later by Foskey, who's able to show that actually these extremizers are just constants up to the modulation symmetry. The dichotomy is also resolved when dimension is equal to 1, Q is equal to 6. Again, a nice even exponent. This is work of Shao, and he shows that extremizers exist and are, again, infinitely differentiable. In general, we think that the extremizers should be constants. Constants are a solution to the Euler-Lagrange equation. for all of these cases, but we don't know whether they're local maximizers, not maximizers, or actual true global maximizers. So Carneiro, Oliveira, Silva, later we're able to tackle this case where Q is even, right? We keep our even exponents that are very nice, and P is sufficiently large given the dimension. In those cases, they're able to show that constants are indeed extremizers. And more recently, Oliveira, Silva, and Kilodron were able to look again here at P equals 2, Q is an even exponent, and low dimensions, and show that, again, constants are extremizers. So there's nice results when we have strong arithmetic assumptions on the P's and Q's, but much less is known more broadly. I also want to mention these are not the only results in sharp Fourier restriction, even for the sphere. There's some really nice results of Giuseppe Negro and Matteo Souza. I just don't have time to go into details on. Questions on the history? So the two most important papers are these ones by Fanella, Vega, Visilia, when P is equal to 2, or Franklin and Sabine, P is equal to 2, and on the scaling line. And what do these two papers have in common? Well, the technique that they're using is a profile decomposition. Franklin and Sabine don't prove it explicitly, but they give all of the sort of results that you need to state what's called a profile decomposition. So I'll show an example of what I mean by that in a minute. I'm not going to say much about sharp Fourier estimates off the sphere because there's a huge body of literature, but I do want to highlight two papers, the first by Betsy Stovall and the second by Shandon Biswas and Betsy Stovall, looking at extremizers in two other cases, so parabolic restriction and restriction on the moment curve. And again, in both those cases, they're able to use profile decompositions to show that extremizers exist without this restriction that P is equal to 2. But they're on non-compact manifolds. So what are we able to prove? What are our results? We're looking at sharp extension for the sphere, and we're asking about existence of extremizers. We can show that if the extension conjecture holds, we're certainly not making any claims about whether it does or not. And we have some convexity. So Q has to be larger than P. In that scenario, non-concentrating sequences have subsequences that converge modulo the symmetries. So that gives us sort of the same dichotomy result. Either extremizing sequences have some subsequence that you can extract that will converge, or concentration happens. And off the scaling line, we're able to resolve that dichotomy and say extremizing sequences actually don't concentrate, so extremizers must exist. I'm going to put up the two different cases of our theorem separately. So what do we say off the scaling line? Off the scaling line, we get existence of extremizers everywhere in this blue triangle, assuming the restriction conjecture holds. And so it's the open triangle. We can't address the case where P is equal to Q, and we can't address this result. It doesn't refer to the scaling line, or P is equal to 1. But we get existence of extremizers, we get sort of pre-compactness of extremizing sequences. And this is the sense in which I mean that extremizers exist more often than not. We have succeeded in shading in more than half of this trapezoid. So there isn't something probabilistic that's going to appear. despite the title making it sound like that's a possibility. On the scaling line, we still have to deal with dichotomy. We have one of two things happening. Either some subsequence converges modulo symmetries to a function that achieves equality, just like in the off-scaling case, or we have concentration. And I mentioned earlier that Frank, Lieb, and Sabine were able to say a little bit more about what concentration looked like. And we're also able to do that, but only under the even further restriction that P is bigger than 2, which feels a little weird because usually P is bigger than 2 is the hard part of this problem. So that's something I find a little bit unsatisfying about our results, is that somehow we're getting a stronger statement in what's in the more constrained part of the problem. So if the extension conjecture for the sphere holds and concentration is occurring. So what do I mean by concentration is occurring? We have our sphere, we have our antipodally symmetric little neighborhoods, one neighborhood near each pole, and the mass of my extremizing sequence lives basically on these neighborhoods. And as we go deeper and deeper into the sequence, the neighborhood gets smaller and smaller and smaller. The mass gets spikier and spikier. My sequence of functions is converging to essentially a Dirac delta at these two antipodal points. But of course, a Dirac delta isn't a function, so it's not converging. And but we can even say a little bit more about what these profiles look like. If I just sort of chop off the picture and look in that neighborhood, the difference between the sphere and the parabola doesn't show up. Right? I've got a surface with full non-vanishing Gaussian curvature. And so this extremizing sequence on my sphere actually has to really look like an extremizing sequence on the parabola. And on the parabola, we would have the extra advantage of a scaling symmetry. So we'd be able to scale this back out to full size and see this sequence actually converge to a function, and extremizers would exist. And they do in fact exist on the parabola, but we're not guaranteed that in the setting of the sphere. So if concentration is occurring, there exists a subsequence which, in quotes, converges. It's getting closer and closer to this sort of pair of antipodally symmetric functions near each pole, which near a single pole look like the pullback of an extremizer of parabolic extension. And this function is, as I said, antipodally symmetric. It looks the same near each pole. But we can't make such a strong statement below P is equal to 2. I think it's true on a neighborhood below 2, but doesn't go all the way down to P is equal to 1. And the P is equal to 2 case of this theorem is due to Frank, Lieb, and Sabine. Questions? Halfway through. So what I want to talk about for the rest of the talk is how we prove these statements. The proof is via profile decomposition. So this is a tool from PDEs, or I think of it as coming from PDEs, which sort of starts with work in harmonic analysis of Lieb's, but then Leon's refines it into this concentration compactness method, and that becomes profile decompositions. Before I get to actually stating a profile decomposition, though, I want to say how we rule out concentration for the off-scaling case. that we're thinking about are inequalities. They're in this trapezoid. And for the purposes of ruling out concentration, I can actually be anywhere in the trapezoid. So my assumption is that Q is in the range where I could hope to have the restriction conjecture be valid, and we're below the scaling line. So if I take a bounded sequence, I want to argue that if it extremizes, it doesn't concentrate. What does it mean to not concentrate? We need to be a little bit more quantitative. So what do I mean by not concentrating? I mean that if you look at a set where the function is large, that portion of the function isn't contributing much to the LQ norm of the extension. So I look at the LQ norm of the extension of F on any subset of the set where the values of Fn are very big. And we see that as my notion of very big gets even bigger, that limit goes to 0. So the portions of the function that take very large values are not contributing to the extension norm. And that's going to rule out these concentrating sequences for me. How does the proof go? The proof is Holder's inequality. And this assumption. So we're on the interior of this trapezoid, which tells me that there's some neighborhood around it where I have a true valid restriction inequality. And in particular, I can pick an R that's a little bit bigger than P that works for the same Q. And we use this extension estimate to bound my function times the set where the values are big. And now I have an R that I can trade for a P. And I pick up a favorable term based on the size of this function, just from Holder's inequality. So as M gets bigger and bigger and bigger, this goes to 0. And this gives me this bound that concentration just can't happen. So that's the only real proof I'm going to give in this talk. It's nice to be able to get something that's useful from just Holder's inequality. All right. So into the profile decompositions. What is a profile decomposition? It's a harmonic analysis talk. What are we doing? We're taking a function, we're dividing it up into pieces that we like better, right? So what are the pieces that we like better? We take our function and we write it as a sum of profiles. Okay, it's a sequence of functions, but the profiles don't depend on which term of the sequence I'm in. These functions phi j do not depend on n. I just give them a modulation, or you could think about that as sort of a translation in space. So that sum of these modulated profiles plus some remainder is going to be equal to Fn. And I've titled this a spatial decomposition, but I'm taking a function on the sphere. I'm sort of living on frequency side. So why is this a spatial decomposition? Well, the important thing about these profiles and their modulations is that if I fix J, compare it to some other J, so I'm picking two different profiles to compare, and I look at the modulations that I need, those are getting very separate. If I think about these as spatial translations, there's sort of a spatial translation on the extension that is moving very far apart. And what are the profiles? The profiles then are the weak limits of the sequence of functions with the appropriate modulations. And this decomposition has some nice properties. We get nice LQ orthogonality. So I think about this first property as LQ orthogonality. I'm saying that the extension norm is the sum of the extension norms of the profiles minus these remainder terms. And even better, the size of my remainders goes to 0, or at least their extensions goes to 0. Profile decompositions in L2 have been pretty well understood. They make real use of the sort of Hilbert space nature of L2. So here we get a much weaker result when we leave the case P is equal to 2. And where that weakness shows up is that we don't have some sort of nice L2 orthogonality. We have that the profiles themselves in size don't add up to anything bigger than the size of the functions I started with. But notably absent is any comment on the size of the remainders. I don't know. We're not in a position to be able to control the remainders. Whereas for P equals 2 profile decompositions, there's also nice control for those terms. But this is still enough to prove our result about extremizers existing. I know the profile decomposition slide has a lot on it. So are there questions before we see how this plays out in showing extremizers exist? So this is the proof of existence of extremizers. This is my favorite part of things. If you've fallen asleep, now is a good time to wake back up. I really like playing with inequalities and particularly sharp inequalities. And this is where we get to do that. So what can we say? I consider some normalized extremizing sequence. So I've got my FNs, their LP norms are all equal to 1 for every single n. And I know that the LQ norms of their extensions converges to the operator norm. That's what it means for them to be extremizing. So now we use the LQ orthogonality from our profile decompositions. We take our Fn, we write it as the sum of profiles and so forth. And we find that the LQ norm of the function is equal to this sum in the limit is equal to this sum of extension norms of the profiles. That comes from our LQ orthogonality. I want to keep estimating. I want a nice sharp inequality. What can I do? Well, we've got the extension of something. Let's apply our extension estimate. So I trade my LQ norm of the extension for the LP norm of the profile. And I pull out the sharp operator norm. And now I have this sum. I have this weird sum of LP norms, and I have to do something about that. What do we do? Right, we know something nice about the LP norms of the profiles. We know that this has to be bounded by the size of the terms in my sequence. So for my normalized extremizing sequence, this thing is equal to 1. But I have P tilde instead of Q. And what even is P tilde? I don't think I defined that on the last slide. So P tilde is the larger of P or P prime. And this is one of the places where my assumption Q is greater than P is going to show up. I'm going to use the fact that Q is bigger than P to sort of separate this into what I want. Not only is Q bigger than P, Q is always bigger than P prime. So if I have a true restriction inequality, this scaling line is below the line Q is P prime. So we're always guaranteed that Q is bigger than P prime. So we use that to tackle this sum. What do? We pull out the largest of our estimates to sort of the Q minus P tilde. We're left with the P tildes in here. And it looks like we've made something very nice into a gigantic mess, but I promise it's about to simplify. So we knew that this sum was basically 1. There's a little bit of playing with the exponent, but I promise you it works out. So this is no larger than 1. And that tells me that this is no larger than the sharp constant times this size of the largest profile. But the largest profile, if the sum of the profile sizes can't be bigger than 1, the largest profile certainly can't be bigger than 1. And so again, this is less than or equal to 1. And we have a chain of inequalities that starts and ends in the same place. We started with the operator norm of the extension operator, and we end with the operator norm of the extension operator. So this is actually a whole bunch of equalities. And that lets me say some very strong things, right? This largest profile, well, its LP norm was equal to 1. I'm going to call the largest profile the first profile, just to simplify my naming conventions. And not only was the largest profile equal to 1, the size of the largest profile, but so is this sum. No. And if the sum of these things is 1, and the biggest one is 1, there is only one profile. So all of the other Vj's are identically 0. And that is enough to find our extremizers. This phi1, whatever it is, presumably a constant, but I don't know how to prove that, up to modulation. This phi1 is my extremizer. Its LP norm is equal to 1. Its extension in LQ is equal to PQ. And the last thing I want to say is that the sequence of FNs is actually converging to this one key profile. And, well, what did we know? We knew that it was the weak limit of the modulated profiles, but now we also have a ton of information about the LP norms and the LQ norms. And with that information, we're able to upgrade our weak convergence to strong convergence. And so that gives me existence of extremizers in this off-diagonal case. Questions? Sorry, trying to check the time and my clock is not totally obliging with me. All right, so I've got, it looks like about 12 minutes left, and I want to say a few words about what happens on the scaling line. All right, we have off the scaling line, extremizers exist. We have our profile decomposition. What can we do on the scaling line where concentration is not something that I can rule out? Another layer of profile decompositioning, sort of. So we take our bounded sequence, no assumptions on whether or not it's concentrating or not, and we write our function as a sum of important pieces and remainders. And here we have something that looks a little bit more traditional. We get true LP orthogonality. We get the same sort of LQ orthogonality in the limit. And we have small remainders for these extension, for small LQ norms of the extensions of the remainders. So far, I haven't actually said anything. It looks very complicated, but if you just took Fn1 equal to Fn, it would satisfy all of these conditions. R and J would be left equal to 0. So to add some content to this statement, we also get geometric control over the sort of location in frequency space on the sphere of these FNJs. So what's the important property of the FNJs? It's that they're appropriately adapted to my antipodal caps. So for each FN, for each J and each N, there is some axis of antipodal points. And the sort of mass of FNJ is going to live close to those antipodal points with radius lambda nj. I've got a cap of size lambda nj. And the last important thing is what's going on with these lambdas. There's two possibilities. For each j, either every single one of the lambda n's is equal to 1. Concentration isn't happening. My FNJs just live on caps of radius 1, and it's all very boring, or reduces to the case we talked about before. Or we have to deal with concentration, which is the case where the radiuses of these caps are going to 0. And we get even a little bit better geometric control. So in the case where the caps were of size 1, when we didn't have concentration, we knew that the big values didn't contribute much to the extension norm. That was my definition of no concentration. And sort of the same thing happens here. For the sort of appropriate scaling, my notion of too big depends on lambda j, but values of f that are too big conditioned on the size of the cap still don't contribute much to the extension norm. So that's my substitute for no concentration. It's that relative to the size of the cap, there's still some cutoff where big values don't contribute much to the extension norm. And with that in hand, we are then able to run the prior profile decomposition on each one of these FNJs. And then we still have OLP orthogonality, we still have LQ orthogonality, we still have small remainders. So those give us the tools that we needed to prove that extremizers exist. What you find is that only one of these J's matters, and the dichotomy comes from whether it's a J at scale 1 or a J where the sequence of lambdas tends to 0, and I have concentration occurring. So that's what I want to say about our proof. So the dichotomy is coming from looking at these different notions of scale. And I'll end with some open problems. So we have this convexity assumption, P is smaller than Q. We use it both in showing extremizers exist, but also in showing our profile decompositions, which I didn't say anything about the proofs of, but we do also use that there. On the scaling line, it's not a restriction, it's always true. But on the off-diagonal case, it cuts off part of our trapezoid. Once we know that extremizers exist, we are very curious to know, are they constants up to modulation, or is there something more complicated or more interesting happening? What can I say about these functions? If I can't prove that they're constant, can I at least prove that they're infinitely differentiable, as has been done in several cases? And the last thing that I would really like to understand is what's happening on the scaling line. Do extremizers actually exist? Can concentration occur? We know of no examples where it necessarily does, and several where it can't. So I'd be curious. And I'll end there.
Thank you, Taryn, for this very nice talk. Is there any question for Taryn? Or any comment? obviously the fact that Q was greater than P was very important. But can you say something? If you remove that condition, do you have some partial progress, or is there something that you can say?
I really think it should still be true. Exactly how to prove it, I don't have a good handle on, but I really think that assumption is an artifact of our method of proof, not a true barrier.
Yes, makes sense. Any other question or comment? Okay, if not, let's thank Taryn again.
So as I mentioned, I'm at Macalester College. It's an undergraduate only institution. So if people have questions about what that's like, I'm also happy to answer that. I don't know if we have like grad students who are thinking about different career paths in the audience.
Okay, that's something to keep in mind. So we will continue. We will see you next Monday. So I hope everybody has a nice week. If there are no more questions or comments, I think this is a good moment to stop. So see you later.